Hello, welcome to the video demonstration for the third assignment in AI, which is the n-queens problem. We are going to solve the n-queens problem by using three different algorithms: the DFS, hill climbing, and genetic algorithms. So first, let me go to DFS. So I had a function which will print out the outputs for all of these algorithms in a standard format, which is named search here. Uh, so okay, so here is search. So I'll print out what the algorithm's name is. It will start the time measurement and call the function, and then stop the time measurement and print out the results. So first I was going to see for DFS. In DFS, we should have a configuration that allows us to change whether we want all the solutions or just one solution. So suppose we want all the solutions, we create an empty list, and this frontier is the stack where we put the nodes, and here a node is just a configuration of the board. It doesn't need to be the whole configuration, like just one queen or two queens could be a configuration, and that would be a node. And in this depth first search, we're going to go down a branch. Say if the first column is 7, then we go down that branch and find further nodes. Further nodes could be child nodes could be like the second node is 6, the third node is 5, and so on. All these child nodes will be checked if they are the goal state. So this function, let me go to this function. So for each node, we're going to check if it is the goal state. And the goal state is that there are no conflicts and all the queens are placed. So if some of the queens are not placed, then this condition will be triggered and it will return false. Because we initially set everything to -1, and if anything is still -1, then it's some queen has not been placed yet. So it's not a leaf, that is, it's not at the bottom of the tree, it's just upper node and it's not been completely filled, so we return false here. If everything has been filled, then we look if there are any conflicts. And if there is no conflicts, then we return the opposite of that. So if we have 0 here, we'll get not 0, so we'll return true. Else we'll get a false or 0 return. So with this goal state, we check if the number of conflicts is 0 and if it's a complete formulated state. And if that condition is satisfied, we go and add it to the solutions. If you want just one solution, we just directly return this whatever we got from this goal test. And if you want all the solutions, instead of directly returning it, we append it to the empty list we created. And finally, after finishing this loop, we return the list of solutions. So that is DFS. Both variants have been covered. Now let's go to hill climbing. We have three variants in hill climbing, and all the three are almost the same. Only the way in which we count the number of conflicts is going to differ. So this is our hill climbing function. So in hill climbing, we first start with a random board, and I wanted to all the three variants to be comparable in the time. So I started with the same random board. I created a random board and passed the same board to all the three variants, just so that it can be easier to compare the time, but it's not actually necessary. So let's go back to hill climbing. So for this, I have created some supporting functions. They are to first to generate a random board, or to just fill in random numbers and create a list of our required size. And then we have find neighbors, which will vary the indices one by one and change the values stored in there, and create a list with all of these neighbors and return that list. Then we have count conflicts. This one is used to count all the conflicts on the board. I will run this and then explain because it will be easier. I'll run this for 8. So now I can use this board to explain this code. So for count conflicts, I first initialize the number of conflicts to 0, and then for each index, I measure the number of conflicts. So for 0, if we see here, we have to see whether there are any other queens in the same row, if there are any queens in this diagonal, and if there are any queens in this diagonal. So first we should check if there are any other queens in the same row, and if there are any in the diagonal like this and in the diagonal like this. Here, these two will measure the two diagonals, and I only check the indices that are higher than the one we are currently checking. So if I'm checking for index 3, I don't compare 3 with these 3, I compare with only the ones after it, so that we don't count it twice for each path. Then I have count conflicts at index. This is very similar to this one, but instead of doing for the whole board, I just count for one particular index on both directions and return the number of conflicts for that index. Finally, we have count conflicts for the second improvement function. In this one, what we do is we measure the number of queens in each row added together, and then we take each diagonal. So for left diagonal, we take this diagonal, then this one, then this one, then this one. Like that, we take all the diagonals and add the number of queens in each one. And again, for right diagonal, we take this one, this one, this one, and the ones on this side. We take all of them and add the number of queens in each diagonal together. And if we have more than one queen in a diagonal, we have to find the number of conflicts and then add them all together and return the number of conflicts. So, so what do we have in this hill climbing function apart from counting the number of conflicts? So first, we take a random board, count the number of conflicts on that board, and then find all its neighbors and count the number of conflicts for all its neighbors. And we choose the whichever neighbor has the lowest number of conflicts. So this is just the conflict counting code. We take whichever is the minimum number of conflicts. If the number of conflicts are at the current board is the same as the minimum number of conflicts for all the neighbors, then we go for a sideways move. So the else statement, which is actually the regular condition, that is, we have a new neighbor which has a lower number of conflicts. We just change board to the new neighbor and we update the number of conflicts to the new value. If we have the current number of conflicts the same as the minimum number of conflicts for all the neighbors, then we take a sideways move and we go to any of the neighbors which has the lowest number of conflicts in the neighbors. But this might lead to an infinite loop where we just choose the same pair of neighbors again and again. So to avoid that, I have a list of boards that have already been tested, and I try to avoid the boards on this list. But if all of them have been tested on that same plateau, then I just try to choose a random one from that list and hope that one of the neighbors will lead me out of this place, out of the plateau. If I'm looping over here for 100 times and get 100 sideways moves, then I can start again from a new random board and then move from there. So this covers all the three hill climbing variants. The difference between the three variants is that in first one we just count the conflicts by the first function, just regular counting. We take each queen and measure how many conflicts it has with the other queens. And for this first improvement, we store what the number of conflicts is for the previous board, and then we take a particular index, whichever one we are changing. Since we are changing only one index for a neighbor, we will have only one. And we take that index, we find the number of conflicts, we find the whole number of conflicts, and we subtract the whole number of conflicts and add the new number of conflicts. So for first improvement, we find the old number of conflicts, new number of conflicts, and subtract the old and add the new. And in second improvement, we just take the whole board and count the number of conflicts by using this method. We add out the number of queens in the row, add the number of queens in a diagonal, and find the number of conflicts from there. So, so we have covered all the three hill climbing variants. Now the last one is the giant algorithm. This code is heavily based on the code provided by KeyCodes on GitHub. So I just changed the knapsack problem to the end queens problem, but otherwise most of the code is just the same. So here for genetic algorithm, our main function is this run evaluation function, and here we first create a population. This population is just a set of random board configurations. They don't have any specific conflict numbers or whatever. They are just randomly selected. And then that population is sorted according to the fitness function. Here the fitness function is the number of conflicts. Uh, the same, I use the same count conflicts function that I used for hill climbing. The basic one, not the improvements. So I use that basic count conflict function to find as a fitness function here. One of the major differences between the fitness function used in the knapsack problem given by KeyCodes and the nQueens problem is that in knapsack problem, the fitness function needs to be maximized, and for the nQueens problem, it needs to be minimized. We want the minimum number of conflicts and preferably zero number of conflicts, so we have to take care of that. So we first sort our population that we created here, and then if we find that we already have reached the fitness function, that is if we have already some board configuration that has a zero number of conflicts, then we just take a break out of this loop and say that the first element, that is zeroth element of this population, since we have sorted it, that element should be the one that fits the fitness function. So we check that one, and if it fits our condition, then we just get out of this loop and give that as a result. If we don't have a configuration that satisfies our condition, then we select the top two elements. Say the first two board configurations have 1 and 2 conflicts respectively, for an example. Then we select those two and send them to the next generation. And among the rest of the population, we use the selection function, which weighs on the probability. Wait, how was it? Yeah, it takes a weight of probability for the based on the fitness function. I used it as an inverse because again we have our fitness function has a lower value than higher probability, so I inversed it. And where was it? So by using that selection function, we select some parents and then create offspring for them. And some of the offsprings may undergo a mutation depending upon the random probability. It may or may not get mutated. Here it is. We get a random, we fix our border like 0.5, and if our random probability that we get is above 0.5, then we don't mutate our genome. If it is less than 0.5, then we mutate and change one index of the genome or the board configuration. So then we have we have the mutation here. So all of these offsprings are added to the next generation. Again, with this next generation, we go up here and again sort it and send the best two to the to that next generation. See, also we check if we have already satisfied our condition. If not, we just loop again and try looping again and again till we either find a board configuration that fits our condition, that is, has zero conflicts, or we end up reaching the generation limit. I have put a generation limit of, actually, I thought I put 1000, didn't I? Yeah, in the search, in the function call, I put it 1000. And so here, let us look at our function call. I had a population size of 100, and fitness limit is obviously 0 since we want 0 conflicts, and the generation limit is 1000. So once it reaches 1000 generations, my program will end whether I get the optimal configuration or not. So it depends a lot upon chance, because there's a lot of chance introduced, like the mutation, and we cannot guarantee that we'll get the optimal configuration from this algorithm. In some runs, I got the result within like 10 generations, but in sometimes I reached the 1000 limit and just didn't get the optimal configuration. So let us look at the output. First, let us look at the 8 size output. Okay, so for each of the results, I created the uh, plot using the function given in the search.py on the in the book code, and so this helps us to easily visualize what the configuration is and how many conflicts we can manually check it. But for now, let's hide it. Let's look at the written output. So first we have DFS, and this is the result for a single solution. And then we have all the solutions. Like there are quite a lot number of solutions here. Let's go back. So this one has taken 0.0009 seconds, and this one has taken 0.04 seconds, which obviously, since we have found a lot more solutions, which has taken a lot more time. And then we have hill climbing. With the basic variant, we find a solution, and it has taken 0.003 seconds. And then with the first improvement, again, we have the same solution. This is why I used the same random starting board for all the three variants, because the number of steps would be same for all of them, and I can compare how much the time varies because of the improvements. So here we can see that this one has 0.003 seconds, and this one is 0.0003 seconds, which is 10 times faster. And then we have the second variant improvement. Here we have 0.0019 seconds, which is faster than this, but it seems to be slower than the first improvement. I don't know why, but yeah, we got the same solution again. Then we have the genetic algorithms. Um, so here we have sort of generations. You can see that the average fitness sort of decreases. We have 8.24 at the first, 20 generations, and 30 generations. Oh, okay. At 51 generations, we have finally got our output. That is, we have got the number of conflicts as 0, and this is our result. And this has taken 3 seconds. This is quite longer compared to the other algorithms, but since we have gone through a lot of generations, this one has taken the most time. In some runs, I got it within 10 generations, and it was a lot faster. So we reached the end for the demonstration for the NPINS problem using these three algorithms. Thank you.